So we learned these electromagnetic waves travel with the velocity of light in vacuum. So this is 1 upon mu 0 epsilon naught. But when these waves are in a medium, in that time this velocity is now 1 upon under root mu epsilon. So this is the velocity in a medium, and we already have seen that this velocity is always lower than velocity of light. But since the velocity of light is such a fundamental constant, such a good constant, that we have measured the unit of length, that is meter, in terms of velocity of light, because we can measure time very precisely. So we have measured, or we have defined meter in terms of speed of light. After that, we have seen these waves can show different type of phenomena that are associated with waves, very similar phenomena like diffraction, reflection, polarization, etc. wave phenomena. That's why we can say these are electromagnetic waves. The fact that electromagnetic waves are polarized, so polarization of phenomena is a phenomena that we will learn in chapter 10. So this is a very important phenomena which is done to electromagnetic waves, can be easily seen in response of a portable AM radio. So here it is written AM radio. So radio comes in two variants, AM and FM. Now we have mostly FM, we don't have AM, but previously there was AM radio. So AM is amplitude modulation, this FM is frequency modulation. Now we have mostly FM, but if we have some AM radio, that means amplitude modulation radio. So in that we can see this phenomena of polarization. So this can be seen easily to a portable AM radio to a broadcasting station. How can we see? If the AM radio has a telescopic antenna, it responds to the electric part of the signal. So suppose this is our antenna. So this will respond or this will catch the electric part of the signal or electromagnetic wave. When the antenna is turned horizontal, suppose we put it in horizontal direction, then what happens? The signal will be greatly diminished. In this case, almost no signal. In this case, almost all of the signal are catched. Some portable radios have horizontal antenna, usually inside the case of radio. So now if we have horizontal antenna, in that case, which are sensitive to magnetic component of the electromagnetic wave. So we have already seen that electric field and magnetic fields are perpendicular to each other. So if this is the direction of electric field, this is the direction of the magnetic field. So this horizontal antenna will catch the magnetic field. So this will catch the magnetic component of the electromagnetic wave. Such a radio must remain in horizontal in order to receive signal, because we have set our radio to be in horizontal. If we make it vertical, it will not catch the signal. So what we learn, suppose there is an antenna type which catches the electric signal, electric component, then we used it vertically. If we make it horizontal, there will be no signal. If we have designed our antenna such that it should work horizontally, then it will not work in vertical mode. In such cases, response has been depend on the orientation of the radio with respect to the station. So what we see, the response depends on the orientation of the radio with respect to the station. Now, do electromagnetic waves carry energy and momentum like other waves? So our question is that, is there a momentum or energy associated with electromagnetic waves? Answer is yes, they do have the energy and momentum. So in chapter 2 we have seen, in a region of free space with electric field E. So there is a space where there is an electric field. So what is the energy density associated? Energy density is epsilon naught E square by 2. So this is energy density. It is not energy but energy per unit volume, energy density. Similarly, as seen in chapter 6, associated with magnetic field B is a magnetic energy density. So what is magnetic energy density? It is B square upon 2 mu naught. So this is magnetic energy density, this is electrical energy density. So we have two type of energy density. So how can we get? We have already learned if we replace E by B. So what we will get? So in this formula what we get? Epsilon naught B square upon 2, and for magnetic field this epsilon naught is replaced by 1 by mu naught. So when we replace this, so again same formula, B square upon 2 mu naught, same formula for magnetism we get. So magnetism and electricity or electrostatics are both very common, both are symmetrical. As electromagnetic wave contains both electric and magnetic field, there is a non-zero energy density associated with it. So what we can see, we have already seen that an electromagnetic wave have both electric and magnetic field. So there is non-zero energy density associated with the electromagnetic wave. Now consider a plane perpendicular to the direction of propagation of electromagnetic wave as given in 8.4. So let us see. So in 8.4 figure we have seen a wave going on. So wave was traveling in this direction, and this electric field was traveling in one direction and magnetic field was traveling in perpendicular to both of them. So this was our wave. So what we do, we put a plane, this plane is perpendicular to the direction of propagation. So let me show this wave just by this line. So this is our wave going and there is a plane. So this is our plane which is perpendicular to this propagation of this wave. If there are on this plane electric charges, so we suppose there are electric charges on this plane and wave is going perpendicular to this plane. Electric charges, they will be set and sustained in motion by the electric and magnetic fields in the electromagnetic wave. So what is the meaning of this? Since this electromagnetic wave has this electric field and magnetic field, so these components, electric and magnetic field components, will make these charges in motion and will sustain their motion. The charges thus acquire energy and momentum from the waves. So if they get some kind of motion and sustaining their motion, so what we can see, the charges have acquired energy and momentum from the waves. In that case, the momentum and the energy in the charges has come from the waves. This just illustrates the fact that an electromagnetic wave, like other waves, carry energy and momentum. So now we have seen that electromagnetic wave carries both energy and momentum. Since it carries momentum and electromagnetic wave also exerts pressure. So we know when there is some momentum, there is also pressure, and that pressure is called radiation pressure. The pressure exerted by these electromagnetic waves are called radiation pressure. If the total energy transferred to a surface in time t is u, suppose we are saying the energy transferred in time t, this time t can be any time, this is the total energy transfer. It can be shown that the magnitude of the total momentum delivered to this space for complete absorption is equal to P is equal to U by C. This is the momentum that was absorbed by the surface. When there is a complete absorption, not partial absorption, if this complete energy is transferred to the surface in terms of momentum, this momentum is energy upon speed of light. When sun shines on your hand, you feel the energy being absorbed from the electromagnetic waves. Your hands get warm. So we have already seen that when sun shines on our hand or on our body, we feel warm of that. Electromagnetic waves also transfer momentum to your hand, but because C is very large, the amount of momentum transferred is extremely small. So we have seen this P is nothing but U by C, but the value of C is very large. That's why we don't feel a very large momentum. So apart from this energy, we are also getting some kind of momentum, but since this C is very large, we don't feel this or this very small momentum, and you do not feel the pressure. Why do we not feel the pressure? Because this velocity of light is very high and this radiation pressure is very low. In 1903, the American scientists Nichols and Hull succeeded in measuring the radiation pressure of visible light and verified equation 8.12. So these scientists Nichols and Hull verified this experimentally that there is some radiation pressure and this formula is correct. It was found to be of order of 7 into 10 to power minus 6 Newton per meter. So here you can see this pressure is very low pressure. This pressure is very low pressure. Thus on a surface of 10 centimeter square about your hand, 10 centimeter square is about the size of your hand, the force due to radiation is only 7 into 10 to power minus 9 Newton, which is very less. The great technological importance of electromagnetic wave stems from their capability to carry energy from one place to another. So what are the importance? They can carry energy from one place to another. So this is very important. The radio and TV signals from broadcasting stations carry energy. Light carries energy from the sun to earth, thus making life possible on earth. If the electromagnetic radiation could not carry energy, life on earth was not possible.